All right. You are basically going backwards, like we said. And we're going to have to introduce some notation, not just some notation, but also some terminology. Now, a differential equation is an equation of a function involving its derivative. For example, simple as that. Okay? It is an equation that involves a derivative. This thing could be as complex as anything else you could imagine. You could say, for example, now, in this case, I'm saying that the slope of my function is 2. What would a function like that be? What would a function that would have a slope of 2 be? It would be linear. Specifically what? What's the function? Y equals. If I were to go ahead and say that y equals 2x, this in reality is an example, because in fact, if we look at this, if that's all right, 5 to it, right? I mean, I still haven't messed with the truth that I do know. If I know that that's a true thing, adding 4 onto 2x is not going to make it a false thing, correct? So what we need to realize is that there is a general and a particular solution to a differential equation. And we add a plus c onto the function. And call this the general form, or general solution. Now, if I had said something like, and the point passes through, and the line passes through a particular point, right? Then I would be able to solve for c. Like if I had said, for example, that the derivative is equal to 2 and it passes through to 4, or better, 2. Okay. Now I can go ahead and find the c for this particular equation. Okay, so then we would be able to go ahead and find our value of c. And we would say that 6 is equal to 2x plus c. Oh, sorry, x is now 2. So now 6 minus 4 equals c, and c equals 2. And now we can say is 2x. What happens is we have a family of functions that all obey that derivative. And we really don't know which one it is, unless we have some more information to find the particular one. So in your integrals, when you're doing an indefinite, you're going to have an answer that plus c at the end of it to represent. Because the 0.24 is really better there. You know, now let's get my slope to be a little bit more realistic. So, you know, here, at this point, then I know the this one. Okay, but you see, right, that we have. It's a general solution. It's not the particular solution. All right, so how do we do this? Okay. If I had, say, for example, if I had that, now what I want to do is I want to figure out what function that when I take a derivative of it gives me this guy. So just like in a derivative, we took apart each term. If I wanted to take a derivative of some all edit terms, I could take a derivative of each individual one, right? So here's the notation piece. I'm moving the dx over to the other side, and now I'm going to introduce the integration notation. It looks like an elongated S, and in fact, that's why it comes from the original idea of taking an infinite sum. And that was the part that I really think that IB dropped the ball on, because in order to really understand what you're doing here, you have to understand the Riemann sums and the sums of infinite iterations and you know, taking things apart into an infinite number of rectangles. A lot of backstory to this that IB has slashed out, which gives it. Yeah, if you wanted to. All right, now, by the way, this was to answer your question. This is called the Jacobian. Because it's not just dx. It can be other things in other systems, all right? It could be a dx with other terms thrown in there, okay? This is for a Cartesian system when you're dealing with x's and y's, all right? If I was dealing with polar coordinates or spherical coordinates or cylindrical coordinates, I would have a different Jacobian. This is, let's look at this for a moment. Now, you are saying to me that there is a function out there whose derivative is equal to 1 when I take the derivative with respect to y. Okay? So what could I take a derivative with respect to y and get 1? Y. Plus c. Now, this guy over on the other side, I'm taking the derivative. I was taking the derivative with respect to y, to x over on the right-hand side. So let's look at each guy individually, okay? Looking right here, what could I take the derivative of to get x cubed? Very good. Look at that. We're not done with it. You'd be left. Now, the next fellow. What? that equals 2x. X. And the last one, plain old 5. And let's not forget plus c. Now wait, these may be different c's, right? Now, they're just a constant. I don't know what it is, and honestly, I don't care. But I know that I have constants, one moment. I know that I have a constant on both sides. They very well might not be the same number, but it is still a constant. So what I'm going to do is I'm going to group them all onto one side of the equation and say, hey, I've got a constant, right? Because it could be positive, it could be negative, I really don't know, I really don't care. But I have y plus number equaling x's plus number. And I'm going to group all those numbers together and just call it number. Plain old C. Because I don't know and I don't care. It's just C. Remember, oh, it wasn't this class. But actually, do you remember when you were doing induction proofs and you were doing inequality induction proofs where you said, I'm going to multiply this side by 2 and multiply this side by 10? Right? You could do that because as long as one side was bigger than the other, you weren't breaking the rules of divisibility or inequality. Wow. Okay. Yeah. We're going to talk to Sparkman. All right. Moving on. So, by the way, since we're dealing with an indefinite integral, okay, we're done. If we were doing a definite integral, which is all indefinite integration, we're done at this point. In a definite integral, things would be plugging. Okay. In a definite integral, yeah.
So I have two questions. So what is that long S thing again?
That's the integral symbol.
So it's like the dy of dx.
It's the operator that says, hey, take an integral.
And
yes.
We don't know the two c's.
I don't know what they are, and I don't care what they are, but I know they exist.
So why'd you combine?
Because I don't need to have two unknown numbers. If I think about it this way, unknown number, add them together, still an unknown number. You know? Why not just put them all in one place?
It wouldn't be two c's.
It's an unknown number. You know, and they're not the same size. They very well might not be the same number. You know?
Yeah.
So C sub 1 plus C sub 2
is still, it's, all I'm saying is it's a number. Right.
Yeah,
Right. Okay. Let me get some good examples in here. All right. Ooh, fun. So, let's try this. Now we're going to have to pull back some of that previous knowledge. What function that when I take a derivative of it gives me x, 1 over x? What is it? The natural log. It's ubiquitous. Okay. Try this one. Now, what are we going to have here? Let's walk through this with baby steps. 5. Now, we know that we're going to have x to the 4th, right? Right. You can start there. You know that you're going to have final honest to God have. Take the derivative. That 4 comes down, right? So that, and it's not in my final honest to God answer, so we have to get rid of it. And that's why we have that 1/4 out in front. And we still have a 5 out there, okay? Plus c. Now, that 5 doesn't really change this thing. So what we can say is, really, this thing is also equal to that. Okay, these two are equal. It is a property of an integral that you can pull a constant out in front. Okay. All right. Constants are allowed to come out. It's also another property, and we saw it a moment before. We didn't explicitly talk about it. That if well, let's look at this. For example, if we did so, one other thing that we saw was that I can take this guy and I can split him up into separate terms. The sum of the integrals is equal to the integral of the sums. That happens a lot, actually, when you get those kind of things. In a sense, you can think that integration, as well as differentiation, are linear operators. Okay? Linear in the sense that they obey the rules of linearity. Oh, I shouldn't use AD. Okay, that's what it means to be linear. A linear function or a linear operator. Both of those properties are true. A scalar can get pulled right out. And if I take two objects and I act upon them, it is the same as if I acted upon them independently of each other. Okay. Now, notice there is nothing in here when it comes to multiplication of two things. Okay? If I had, let's do this one. Let's do that. What derivative, what function that when I take its derivative gives me sine? Right, because cosine, derivative of sine is cosine, cosine is negative sine. But this is a positive sign. So it needs to be, we need to keep our signs right on this. No pun intended.
Did you say equals? It's just.
Mm-hmm. I lost the dx. I think to lose the dx. Thank you. That was, you know what, when I was a student taking calculus, adding the plus c was the thing I always lost points on. I goofed that when I was in high school all the time. So, yeah. Hey, I can appreciate that. So this, I will say, begins to approach an art form, in a sense. There comes a point when you start looking at these things and you have to say, your toolbox gets bigger and bigger and bigger, and you're able to handle nastier and nastier integrals. Okay. Now, let's try a few. Ooh, fun. Oh yeah, fun. Mm-hmm. Yeah, something plus C. Yeah, that's it. Right. Let's all play school. Yeah, right. Yeah. All right, now our final honest to God answer has to have a, well, it has to have a something in there that gives me the 1/2 exponent when it's done, right? So we add 1 to the exponent. It is weird doing it backwards, but you'll get used to it. Right? And now we have to get rid of the 3/2 when it comes down. Okay? So it is going backwards, right? And you can always check your work. You can always check your work. I'm going to mess it up over and over again by taking a derivative, either on paper or mentally. Okay?
Is it safe to say that for the coefficient, you can just take the exponent and flip it, and it'll all be right?
Yeah, then there might be some simplification involved,
Yeah.
though. Okay? For example, if I gave you right?
Yeah.
So when I do this, I wind up with 9 x to the third times a third plus c, which equals 3 x to the third. Okay? So it is safe to say that you can just put the reciprocal of the exponent plus 1 in front, but that's not saying that it's your last step. There's probably some simplification algebra involved somehow, somewhere. Okay, don't be. All right. Now, what other ones do we want? Ooh, fun.
What happens when you have x squared? Or like 2x?
Oh, composite functions? Okay. This is when things start getting nasty. This is where the art form comes into play. Yeah. Before you start going ape and figuring out where things are and what things are supposed to be doing, okay, before you raise your hand and say, waiter, check, please, first, attempt to simplify and get this thing into something that's a lot simpler and nicer, if at all humanly possible. All right? Because now, instead of walking up to that function and saying, hey, you're a division, instead, now you walk up to it and say, hey, you're an addition. Okay? You've kind of turned the outer wrapper from a division into a subtraction. All right? And now we can simplify a little more. We can do it all together. Okay, now let's go ahead and so simplification really helped. All right. Now we can take the integral of both. So I take this guy, I add 1 to my exponent, which becomes 5 over 2. And what do I have to put out in front? 2 over 5, right? What do I have to put over here? What's his exponent? Positive 1/2, because I added 1 to it. And now I have to put what out in front? A 2. Now, you can simplify, but I would be probably happy with this, okay? But if you did wish to simplify, you could. And in fact, I could pull out doesn't matter.
I thought you.
I have the associative property of, right?
Oh.
Yeah. Where? Oh, wait, can I finish this line?
Yeah.
So this is squared. Is that right? No, hold on, brain damage. Yeah. That's about as far as you could possibly take it.
Didn't you where you did
Yeah. Okay, now you had a question, Becca? What was your... From here to there? Okay. I just combine my exponents. 2 minus 1/2. Exponents, when you multiply the exponents. Yeah, the exponents. And then that didn't change. And then to go from here to there, I did the integration. I added 1 to the exponent. It's the power rule, right? And then, okay. Another set of examples. Ooh. Let's do another simplification.
Can we start there? At least.
Turn it into something a little nicer, right? Um, you could do something like now what is that? What's sine over cosine? Wait, what's sine over cosine?
Oh,
Tangent. Tangent. And 1 over is and does anybody remember their common trigonometric derivatives? Look at your list of common trigonometric derivatives.
That is secant squared x.
Okay.
Oh,
But when I take the derivative of something, do I get tangent secant?
the derivative of secant is
Secant tangent. Secant tangent. Say the word. Yes, thank you. Secant of x plus c. Okay. All right. So let's do a word problem, shall we?
don't tell me there's a relation.
All right, we have a ball thrown upward with an initial velocity of 64 feet per second. Okay. All right. Find the position function giving the height s as a function of the time t. That's an s.
Yeah, I don't get it. Thank you.
You're welcome. More than welcome. Now, the position, okay, now let's go into this a little bit. We have position, velocity, and acceleration. Okay. If I take the acceleration and then take a derivative, okay, with respect to time, I get velocity. If I take the derivative with a velocity with respect to acceleration, I get position. So, and this kind of makes sense. Wait a second. Am I out of my mind? I am out of my mind. It's the other way around.
No, you said it the other way, but that is why I don't write it.
wait, what is your
Yeah, the slope of my, how is my position changing? That's speed. Freaking brain damage, Ronco. Uh,
kind of?
Yeah, yes.
Okay. How is position changing with time? Think about that. If you're talking about where something is and then how it changes with time, how fast is it changing with time? Something moving, that's speed. If I talk about how is velocity changing with time, that's acceleration. Okay? So, yeah, we're throwing an object. Now, we need, the question is specifically asking, we are looking for the position function, giving the height as a function of time. Well, that's, so this is what we've been asked to do. So we take what information we have. Okay? We have an initial velocity. All right? So we can say ds dt is equal to 64, okay, feet per second. We also have an initial condition is equal to 80. Position, height, displacement. Now, right now, at the initial condition, it is. But we have acceleration due to gravity. And I should say, wait, did you make the call you needed to? Okay, all right, that's fine. And I'm just going to be a little bit more specific here. The derivative at 0, okay, when the height is 0, at the initial time. Okay. All right. So we have, let's list them all in one place. We have s sub 0 is equal to 80. S prime of 0 is equal to 64 positive going up. And S double prime is actually it's constant everywhere, assuming we're not going up into the stratosphere, something like that. Okay? And actually, I could even go so far as to say this. So, now, when we needed to go and find these as functions, we have to remember that C term, because that's where things come into play. So we have the d squared s dt squared is equal to negative 32. Okay, so now we're going to integrate that. That's acceleration due to gravity. 32 feet per second. Yeah, it's physics. Everything falls 32 feet per second when you're close to the Earth. If you're like up in the upper atmosphere, it's slightly less because you're getting farther away from the center of the Earth. Yeah, because it's going down. you guys ever take science class?
This year, man.
I don't want to call it. Our tutor doesn't know that.
She's like, nope, that's how it is. Yeah, learn it, love it.
She says that every time. I always ask her why is it like this. She's like, no, it's just like that. That's
She,
why.
like, she doesn't know. So.
That's a darn shame. All right. So when I do this, I wind up getting ds dt. So if I integrate a double integral, I only get a single derivative. I have, you know, what I'm doing is I'm doing this derivative with respect to t, and I get one out of it. The double, if the second derivative, if it is confusing you, you can leave it out, and you could simply just say the following. Actually, not a 0 of t. And you can just feeling integration. All right. Let's get this back to something a little bit simpler. Now we have an initial condition that we have to care about. We know that at 0, this function is equal to 64. Right? So now c is equal to 64. So this is an acceleration function, sorry, a velocity function. I know. What? No, that was position. We're fooling with velocity now. And we can do the same thing again to get position. Okay, we're going backwards now. Again. So when I take a derivative now, was it 64? Oh, yeah. Thanks. Typo. All right. Now, simplifying, plugging in my initial condition for the height. There is going to be a homework assignment posted, and it's going to be hefty. Yep.
The homework's going to be
No. Homework will be due next class. You have a day off, a full day off. This episode of The Bronco Show has been brought to you by the Indefinite Integral and the constants C1 and C2.